Hey there, everyone. My name is Ryan Schul. Welcome to my YouTube channel. So, in the narrative today, I want to take a look at real-time elevator dispatch optimization in a high-rise building. So, this came up on my radar, I don't know when, maybe uh, 18 to 24 months ago. I was looking at a couple elevator algorithms and trying to understand how does the elevator system know how to dispatch the car that is closest to you that doesn't have maximum capacity all filled up already, right? If they send a car that's one floor away, but it's totally full and you can't get in, what's the point of that, right? It wastes everybody's time, everybody on the elevator and yourself, and it's delaying other elevators that could come and pick you up. I've seen it happen many times. I don't know if that's a bug in the system or what, but don't just send the closest car, send the closest car that actually has some capacity for the person to move in. And I understand if there's space for one more person and on the floor that's where the button is hit, maybe there's three people getting in. Like the elevator doesn't know that unless maybe there's a camera on that floor and they can um, use some kind of AI to determine three people are waiting. There's one open spot in this elevator. We can't send this one. So we'll send the next closest one that has capacity for three people to get on, or whatever the case is. Like, I don't know exactly how that works, but I tried to dig in and try to understand it to the extent possible, and I'll share my findings with you here. So I'm going to create a prototype with a real-time dispatch. I'm going to assume this is a 30-story building, 5 elevators. This is a real scenario in a building that I used to live until about 6 months ago. 30 stories, 5 elevators. Sometimes the car would come quickly, sometimes it was very slow. I don't know if there's any like logic to the system. I'm not sure there was. I never saw any evidence of that, but it seemed like it always took some time for the elevator to come. It was rarely there waiting for you, or rarely came in a few seconds. There's always some kind of delay. I don't know why. But let's set this scenario. Look at the nearest ETA. This is the estimated time to arrival. Um, Anti-bunching, so we don't want elevators like pretty close to each other. We want them spread out. So one at the top, one at the bottom, 3 in between. If it's a slow day, if the elevators are moving, then they're moving all over the place, right? If it's a slow period, maybe early in the morning, late at night, overnight, we can disperse the elevators so they're spread around. So what else? 30 floors, 5 cars. We're going to assume about 2.5 meters per second. That is the distance that the elevator can travel. About 1.2 seconds per floor. 2 seconds for the door to open. 2 seconds for the door to close. Right. So it's time. There's always some kind of minutia that you have to account for and keep track of. Right, because it all adds up cumulatively. 2 minutes open, or 2 seconds open, 2 seconds to close. That's some time. 2 seconds to move a floor, um, or what? 1.2 seconds, right? So you have to accommodate or account for all these variables. Okay, bare minimum time, maximum time that somebody's willing to wait for an elevator. That could be maybe 4 to 5 minutes. The minimum time would be almost instantaneous, right? Or a couple of seconds, maybe. So we're going to try to assimilate all these different criteria and all these different parameters into this problem and try to contain the problem and solve the problem as well. Okay, so we have destination aware boarding and aligning. So this system that controls the elevator dispatches and picking up all these people and requesting elevators in different floors. We're going to set up the problem and try to solve it that way. 3 dispatch policies are going to be assumed, and diurnal weekly traffic, and we can assume that there are rush hour contingencies or rush hour scenarios, I guess. So between probably 8:30 and 9:30, there's going to be peak usage Monday through Friday. Weekends are going to be different. Weekends are going to be much more variable. Weekdays are going to be much more predictable. What else? Destination boarding times, dispatch policies, SLAs, service level agreement. So you'll probably have a contract with the elevator operator or the company that sets up the system, right, and dispatches the elevators in an efficient fashion. You probably have some kind of SLA agreement. They have a contract where they have to provide minimal levels of service to the customers that use this elevator. All right, so here's my parameters: 30 floors, 8 cars, capacity is 20. Lobby, you could have multi elevators, like actually 5. This is gonna be 5. You could have um, 3 elevators in the lobby, right? If it's a slow time, probably one at the top, and 1 in between or 3 in between, right, scattered around. And the SLA agreement is 180 seconds. So 3 minutes should be the maximum time for a person to wait for an elevator. Okay, if you cannot meet those SLAs, if it exceeds that 180 seconds, then the company has to pay reparations to the building, for delays, for unnecessary um, delays for people to use the elevator. So that's the scenario. I set up some passenger classes over here, car classes. So how our car is going to be dispatched in an efficient fashion, how our passengers going to call the car and board the elevated car. I have set up several UDFs here. This is a user-defined function. So hourly profile, up base and down base, if less than 8 and less than 10. So this is 8 a.m. to 10 o'clock in the morning. This is a peak time, Monday through Friday, and 7 to 19. So 18 is 1600 hours. This is 5 p.m. to 7 p.m. There's going to be anticipated higher demand Mondays through Fridays. So there are definitely like simulations or scenarios that we can anticipate, right? Weekends is going to be more diverse usage. Weekdays is going to be more consistent and persistent type of usage. So we can bake that into the UDFs and the mathematical calculations that we have to undertake here. So what else? We have ETA, estimated time of arrival over the plan. We're looking at the current floor, the door open. This is like 2 seconds to open, 2 seconds to close. There's a short time to go between the floors, right? And there's a time if you're going from the top down to the middle floor, or middle to the bottom, or bottom to middle, or bottom to the top, right? There's always like a calculation and duration of seconds to account for the time that it's going to take for that elevator to arrive, right? So moving on here, ETA, if insert, again, we're looking at the car, stop floor. What else? We're looking at in range, the plans of the elevator. We're looking at the length of the elevator, adding one to get to the next floor. Okay, we're going to have to go wherever you're going. We're going to go up one. You're not going to get on the elevator and get off at the same floor. So we account for that. Dispatch policies. So we have to send the nearest elevator most of the time, but not all of the time. The exception is if you have an elevator that's very close and the ETA for this elevator is maybe 2 to 3 seconds, give or take. That's the closest elevator. But if it's filled to capacity and you can't take another passenger, don't send that elevator. I've seen this happen before. Elevator comes totally full, you can't get on. You're wasting everybody's time in the elevator and the person standing on the floor expecting to get on the elevator, but they can't because there's no room. If the elevator is at capacity, don't send that elevator. Okay, that's a bug in the system, or it's a shortcoming, or somebody never accounted for that. I've seen it happen countless times. If it's full, don't send the elevator. Send the next closest elevator. Okay, that's your ETA, estimated time for arrival for the nearest elevator that's not at capacity. Okay, so that's a problem. Fix it. You know who you are. You guys designed the thing. That's a gap. That's a bug in the system. Don't send a full elevator. That's useless. Okay, so the dispatch is the nearest ETA that has some capacity. If at capacity, return the cars, the time now. Otherwise, dispatch zoning, the next closest elevator. SLA, this is a heuristic. Heuristic is basically we're making an approximate determination about the outcome of a specific mathematical equation or a specific mathematical requirement, but it doesn't have to be absolutely precise. But the heuristic is going to be very, very, very close, and it's going to run significantly faster than a model or an algorithm that will generate extreme precision, but might take significantly longer to run. So a heuristic example would be, can you get within 1% of an accurate calculation or an accurate outcome, or one fraction of a percent closest to the actual outcome, and you can solve the problem in 5 seconds, versus you want an absolute perfect mathematical outcome with 15 decimals of precision, but it's going to take 8 to 10 hours to do the calculation. So all things being equal, I would rather have a close approximation and the problem is solved in 5 to 10 seconds, then wait 8 to 10 hours and get an absolute precise result, right? If it's very, very, very close and it's done in a few seconds, that's good enough for me. I don't want absolute perfection and I have to wait 10 hours for that, right? It doesn't make sense. So heuristic is going to give you a result that's very, very close, not absolutely perfect, but it finishes very quickly, and that's the value add. Okay, so we're looking at the wait time up, wait time down. All this goes into the UDF, right, to do these calculations. The total minutes of the elevator running. DOW is the day of the week, 24 hours a day, 60 minutes per hour. Total minutes, we're going to get the hour up rate, down rate, and the day of the week and the hour that the elevator is operating, just so we know, again, the demand on these elevators. So 8 to 10 a.m. Monday through Friday, and 4 to 6 p.m. Monday through Friday is going to be peak hours. Weekends, all bets are off, right? It's going to be totally different. It's going to be totally random because people don't have the same work demands, the same professional work schedule, okay? So let's get down here to the bottom. We are returning a dictionary. With the customer served, this is a total count of people using the elevator, wait time mean, wait time in the 95th percentile. So 95% of the time, the elevator will come within a certain frequency or less, right? 5% of the time it's going to be longer, 95% of the time it's going to come as expected or faster. The average ride time, the energy that the elevator uses, okay, down is going to use less energy, up is going to use more because you're going against gravity. The total number of stops per floor, and this is stops like going up and down in the building per floor, is going to be 1 to go from the top down to the bottom, or you have to stop 5, 6, 7, 10 times, whatever, and the minutes that it takes for the elevator to arrive. So that's the scenario. I'm going to go ahead and set up in this main function. I'm going to go ahead and run this, Control Enter to run the cell, and I'm going to feed in some basic bare bones information to get the output in a generic scenario here with simulation of seconds, 1 second, seed to start, start hours 8 o'clock in the morning, total number of served, and I want to know on average how many people are served, what's the mean wait time, the 95th percentile, or under, how long is it going to take, the mean ride, the average time you're riding in the elevator, energy used, and number of stops. So we have 791 people served around 8 o'clock in the morning. Without mean time, 15.9 seconds. 95% of the time, it's 51 seconds or less. Every 5% of the time, it takes more than 51 seconds. The mean average is 111 seconds. For all the people to go up or to go down on the elevator on one ride, the energy, 142.3 joules. This is in joules. I assume I didn't define the unit, but usually that's how energy is measured in joules. Stop 747 in this time frame. 788 people are served. The average wait time 15 seconds. 58.9. So this is the nearest ETA. The zoning, right? This is within certain zones or different areas of the range where the elevator serves. 95% of the time, 58 seconds or less. Here it's 51 seconds. So the zone presumably is a little bit broader. The mean is about 93 seconds, so it's actually less here. So the time, overall average time to serve customers is 58 seconds. Here it's lower, but here the average ride time is less, and here it's higher. That's interesting. The energy here used is a little bit less, and the stops is just about the same, just a little bit over. Stops over here. Destination group, 785 people use it. Mean time is 16 seconds, 48 seconds or less, 95% of the time. Average ride time, 92 seconds. Energy is 146 joules, so almost the same as that, and 748 stops. So that's a lot. That's a lot to digest. It's a lot to assimilate, right? We're looking at people served. These are passengers completed, boarded, reached the destination in a 30-minute simulation. The mean wait time is the average seconds from pressing the button until the assigned car arrives. 95th percentile, again, says 95% of the time you're going to wait this number of seconds or less. We saw that right here. So 48 seconds on average, 95% of the time, 5% it goes over. Here's 58 seconds, and here's 51 seconds. 5% of the time it goes over. Energy, computer floor to floor and door cycles. Lower is better, right? The lower we pay for energy, the better. That's common sense. And total cycles across all cars. This is a proxy for the wear and tear on the elevator, right? So let's go ahead and look at a matrix with some calculations here. we're looking at an average day in the week. We're looking at 7 different days, okay? 24 hours in range, 60 times 60, so 60 seconds times 60 minutes. That is going to be 6 of 6, 3,600 minutes. Simulation, 100 hours. Start is day of the week. I think Monday, because Monday Python starts with a 0, goes until Sunday. Sunday is a 6. So 0, 1, 2, 3, 4, 5, 6. That's 7 days. It's always 0 base. Starts with 0, goes until 6, right? So it doesn't really go from 1 to 7. It goes from 0 to 6. The same count of 7, but 0, just starting with 0. Okay, so this is running. Let's give it a second here. Okay, nice. So the data table or the data frame is done here. We see in this simulation here, 7 days, 24 hours in the range. Simulation seconds is 60 times 60, so 3,600 seconds. Again, Monday is 0, Sunday is 6, and 23.59 hours in a day, 24 hours in a day. So we have minutes, days a week, hour, arrivals, boarded, dropped, energy used, number of stops served so far, and the policy usually is the destination. So you go from the origin to the destination, the start to the finish. So people per day, starting on Monday, Monday 0, Sunday is 6. We see here's Monday, arrivals 750, 7,500, 73, 74, 72. On the weekends, it's less, right? So this is probably not a commercial building, probably residential. If it's commercial, I would expect this Saturday and Sunday numbers. Saturday is 5, Sunday is 6. I would expect these to be lower. Could be commercial, though. Could be people going into the office, working on the weekends. 2661. Elevator rides, arrivals, at least. Presumably, whoever goes in is coming out. So arrivals is probably same as departures. 2661, 2604 for Sunday. Again, significantly lower than weekdays, but still getting some usage on the weekends. People per hour, so this is interesting too. So arrivals at midnight, there's probably some people working 24/7. Who knows what? Lawyers, doctors, maybe using the elevator, but the frequency is way lower than normal rush hour. Here we have 4,000, 4,100, 1,200. This is mostly people at work. Some people coming in a little bit late. This is 4 p.m. It's picking up at 5, peak usage 6 p.m., tapering off a little bit, 7, 8, 9, 10, 11. Still getting some usage, but not quite as much, okay? And again, these are the hours throughout the day. So peak is 8, 9, 10, tapering off. 19, 20, 17, that is 5 p.m., 17, 18, and 6, this is 7 p.m., 21 is 9, and 23 is 11 p.m. at night. So we have great looking data frame over here with all our metrics. Looks totally fine to me, plausible. We have the arrivals per day, per hour. So let's go ahead and start creating some charts and plots. I always say picture's worth 1,000 words, right? I can take this to somebody and describe what's happening. It's going to probably take 1,000 words to communicate the message. Same over here. If I show a simple chart and a visual representation of what we're doing here, the person is probably going to say, oh yes, this makes sense, I get it. Totally makes sense here. So this is what we saw. So Friday, Monday, Saturday, Sunday, dips down Tuesday, Thursday, Wednesday, and you see pretty normal usage, less on the weekends. Here is a weekday scenario by hour. So over here, lower utilization during the day, 8, 9, these are the peak hours, right? People are in the office, maybe eating their lunch at their desk, maybe they go out a little bit, around 12, 1, spikes up a little bit down here. I'd say most of these people bring their lunch, they're in for the day, heading out by, this is 4 p.m., so 5, 6, 5, 6. There's a big bump in utilization, and again, down here, it kind of like tapers off, goes off a cliff, actually. So it goes from almost 4,397 at 6 p.m. to 1,350 at 7 p.m. So after 6, most of these people are gone. And this isn't continuous, right? We're putting these into buckets of 24 hours. So I understand the big drop over here. Seems like we're falling off a cliff. But if you had this in more continuous flow, you would see more of a ramp up instead of a big spike and kind of plateaus, quick drop off, but more curvy linear, not linear, and then curvy linear up and down, and you would see that pattern over here. We have the same thing because I hit the button twice. Okay, So that looks good. So we have the charts, we have the times for the elevator. Let's look at one more scenario now. So this is the closest car for trips. I created a small UDF over here, and I'm looking at the destination minus the origin. This has to be an absolute number. So absolute referencing means has to be positive. It can't be negative number. Negative time doesn't make any sense. Just ensuring that, guaranteeing that. Times floor time plus door open, door closed, and the dwell time. This would be kind of like the the downtime or some time, a few seconds, not much, but every minute counts, so you have to account for that. So door open and door closed, I think we said that was 2 seconds. Floor time to get on, I think that was 1.2. All the parameters are at the top. I'd have to look at this again. Door open, door open and close is 1.5, and to get on, or nothing happens for about 2 seconds, and to get on and off, I thought it was like 1.2 seconds. I don't see that. Anyways, so everything is accounted for. Every minute counts for something, right? So, so move down here, and I can tell something is weird here because this thing is jumping around, and it shouldn't be. So let me just refresh the view. Okay, it's a little bit better. Okay, so we have the user-defined function to pick the closest car, and again, make sure that the car has some capacity. If you send a full car, that's useless, waste everybody's time. We are going to enter the origin and destination floor. So origin is the start, the destination is the end. It's going to be a numeric number, a whole number, can't be a percent, can't be a fraction, and another number, right? So the origin, destination, the start and the end of the trip. We are going to look for the closest assigned car, call at floor, ETA to pick up, and the estimated arrival time and destination. So the way I set this up is you can hit Control Enter, and we'll get a prompt from a user. So you can put in the beginning and the ending of your trip in terms of the origin and destination of the floor. Let's say I'm on floor 3 and I want to go to floor 10. So 3, 10, 3, 10. So origin 3, destination 10, enter. So the assigned car is car number 0. We have 5 cars, right? 0 through 4, 0, 1, 2, 3, 4. That's 5 cars. Currently at floor 1, call it floor 3. I'm at floor 3. That's what I want to pick up the elevator going to floor 10. ETA to pick up takes 3.4 seconds for the elevator to get from floor 1 to floor 3, right? It goes about 1.2 seconds per floor. Estimated arrival at destination 13.3. So 1.2 seconds per floor. ETA to pick up 3.4, and to get from 3 to 10, which is 7 floors, 13.3 seconds. Not bad, right? Let's try another one. Let's say we're going from floor 11 to floor 29. Enter. So 11 to 29, assigned car 0. 0, again, is the closest one at floor 1. So again, most of the time you'll see an elevator at the bottom, at the top, to make sure if someone's coming in at the bottom, all the elevators are not at the top, and you have to wait for one to come down. That's just silly. You don't want all the cars at the bottom because somebody is going to be on the 30th floor. Inevitably, they need a car to go up. You don't want to wait for one car to go up because all 5 are down. So you'll stagger them. Some will be at the top, or at least one at the top, one at the bottom, and a few in between. So we'll put one at floor 1. This person's at floor 11. They go into 29. So the ETA to pick up the person from floor 1 to 11 takes 9 seconds. From floor 11 to 29, 26.6 seconds to get from 11 to 29. Let's try one more. Let's say we're on 28th floor and we want to go to floor 1, 28 to 1. Okay, assigned car currently at floor 1. So that's interesting. I would think that the car should be higher up at floor 30 or close to it, but maybe the elevator is busy. This elevator is actually at floor 1, and it's car number 0. Remember, we have 0 to 4, 0, 1, 2, 3, 4, 5 cars. Call it floor 28. Going down to 1, ETA to pick up the person, 20.9, has to go from floor 1 up to 28 to pick up the person, and estimated arrival at destination 44.8. So 20.9 seconds to go up, about 24 seconds to go down. 20 plus 24 is 44 seconds. Okay, so that's my take on the elevator algorithm, assigning cars that are close, that are not fully booked up. You need some capacity to pick up the passengers. And again, I think some kind of camera AI system embedded in this, so you know, is one person getting on the floor? Is it 2, 3, 4, 5? How many people are getting on? If you have mostly full elevator with basically 3 spots, and 5 people are going to get on the floor, don't send the closest elevator if it only has 3 spots because the people can't fit, right? Or, I mean, I suppose 3 people could get on, go shoulder to shoulder, scrunch in there and get down. 2 people have to wait. That's one scenario. Um, I guess you'd have to calculate it. Would that be better to let 3 people get on and make 2 wait, and then send another elevator for the 2, or wait for an elevator that has 5 capacity, 5 openings, 5 spots for these 5 people, and wait for that? Then all 5 can get in and go downstairs. So, I mean, I guess that's debatable. We could use some statistics or some math to figure it out, and maybe it's really um, more of a personal thing. Like, does somebody want to squeeze into the elevator, or they're not comfortable with that? They'd rather just wait for another 10, 15, 30 seconds or whatever and just wait for something that has more space. That's your personal preference. We can't really mathematically represent that. Math can only represent, quantifiable things. If it's somebody has like what is it, claustrophobia, and you're scared of being in a small space with other people, math can't predict that. So that would be a personal decision. The person could say, I'm not going to get in the elevator, it's too crowded, even though there's space, and maybe there's 5 spaces, and this one person won't go in because they have claustrophobia. That's like a whole nother thing. I can't anticipate that or plan for that or model that. You can only model things that are quantifiable, right? So you can't modify people's personality or quirks, right? Or persuasion or proclivity for something, right? So that's it. That's my take on the elevator algorithm. And yes, I understand, like, people aren't typing numbers, floor, origin, destination into a laptop, and then that controls the elevator. But the system could be governed by this type of logic, right? You could program Python inside of the elevator um, um, brain or circuit board or control panel or whatever controls the elevator. Like, I understand people aren't saying on their laptop controlling elevators. I'm just trying to illustrate the point of the mechanics and mathematically and how statistically this should operate. That's what I'm trying to do here. So yes, I know that Python is not controlling elevators from the laptop. So all things aside, from that, that's my take on real-time elevator dispatch and optimizing the whole process. Hopefully that was enlightening and somewhat entertaining, and basically informative as well. So I'm going to wrap it up here. I will save down the source code and I will post that. When I post the video, it's going to go a little bit later today. I'll drop it probably this afternoon. Plan to put down a couple more, and I'll put this one down with the others. Okay, so that's it. I'm going to wrap up here. Thanks for your time. Appreciate that. And I'll see you guys in the next video, which I'm going to drop pretty soon. Take care for now. Talk to you soon. Bye.